Hello, welcome to Predator-Prey Models, Part 2. What we talked about in our introductory example was how we can plot the approximate solutions to this coupled differential equation, since it can't be solved exactly, on a graph using the Euler method. And, sorry, I'm just going to show you that. And notice some of the turning points. So what we noticed here was that as x increases, it reaches a maximum point around here of approximately, oh, sorry, this is at 7,000. Give me 1 second. I'm sorry, that was the right graph. As x increases, it reaches a maximum of around 7,000. And that maximum value, so remember, x was thousands of fish, that value stops as soon as the shark population, our y value, reaches 1. In other words, 100, because our y values were in hundreds. Now, when the sharks reach 100, then our x values start to decrease. Look at this. This goes backwards, and our shark numbers start to increase, but then there's so many sharks and too few fish for them to eat that around here, at this number of fish, which is approximately 1,000, 1,500 or so fish, then our shark numbers start to decline. And we can see that simply by plotting our approximation using Euler's method, just the x and y, just plotting the x and y, we'll get this circular graph. And we can also see that if we plot x and y on the vertical axis with t on the horizontal axis, we see these same values happening. So x, remembers, our fish population. Our fish population reaches a maximum around here, again around 7,000. Oh, that was actually 7,500. While our shark population is around 100. Yeah, it looks like about 100 right here. And notice this is the y value, not the t value. That's what I was getting confused earlier when I was reading this graph. Then the fish population declines until, the fish population declines, sorry, and the shark population keeps on increasing until we get to this many fish, approximately what we saw earlier, and then the shark population will start to decrease because there's not enough fish. And what we actually will notice is that this is a cyclical pattern, all right? So then as the shark population starts to decrease, the number of fish will start to increase. As the fish increase, the sharks increase. As the sharks increase, the fish will eventually start to decrease, and that's going to go on and on and on. So this graph doesn't end here. It's going to be like two sinusoidal functions, right? Going in ebbs and flows. Now let's take a look at another problem, just as another example, and recall how we did some of those calculations, particularly using a spreadsheet. All right, so if we're looking at exercise 12I, which is part of your homework, so you can just do that along with me here. Words are hard. Take a second and read this while I fix my pen. Okay, so we have x dot, as we were familiar with from Monday. We have y dot. We can see these are two differential equations where each variable is dependent on the other, and these differential equations are relative to time. All right, so we're taking the change in x relative to time, x being the what? Rabbits in thousands, and the change in y relative to time, y being the foxes. Now let's find the non-zero equilibrium position for the populations of foxes and rabbits. So usually 0, 0 will be one of those equilibrium points, but there is often another equilibrium point. So as we did in our previous example, we're going to set each of our derivatives equal to 0 and solve. X minus 2xy equals 0, and the other derivative also equals 0. 1.8xy minus 1.5y. All right, I'm just going to factor here. And we know we're going to have x equals 0, but in this case, y equals, what is it, 1/2? Yeah, 1/2. So in other words, 50 foxes. Just jot that down. 50 foxes All right, and in this case, if I factor, I'm going to get 0 equals, now we know y would equal 0, but what would x equals? 1.8 x minus 1.5. Is that going to be 15 over 18? 5/6? So in this case, x equals 5/6, which is approximately, what's that as a decimal? 0.833. So about 833 rabbits. Little bunnies. Okay. This is the non-zero equilibrium point. It's going to be 5/6, 1/2. All right. Initially, there's 750 rabbits and 100 foxes. All right, so they're giving us those numbers in with the units, with the scaling rather that we have. By putting the initial values into the differential equations, state whether the populations of foxes and rabbits are initially increasing or decreasing. Okay, so this is a little bit different from what we did the first time. Now, I'll do this up here on this side. So this was A. I know I'm going to run out of space here. Let's put these values. So 750 rabbits, so dx dt is going to equal 0.75 minus 2 times 0.75 times, what is our y value? Initially, 1. All right. And let's just get that calculated. 0.75 minus, oh, okay, that's going to be negative 0.75. Sorry, don't need to calculate that. Okay, so the rate of change of x, of our x variable, rabbits, is decreasing initially. So our rabbits are decreasing initially because we have a negative rate of change. Okay, and sorry, this is still part B. Let's substitute those numbers in for the rate of change of the number of foxes. We're going to have, what is this? 1.8 times 0.75 times 1 minus 1.5 times 1. This is, I believe, going to give us another negative number. And that is negative, 0.15. So, hey, look at that. Actually, initially, our number of foxes is also decreasing. And I say initially because they said initially, so at t equals 0. Okay. Let's take a look at what they're asking in part C. From the differential equations, find the size of the fox population when the rabbit population is a maximum. All right, beautiful. So this takes us back to understanding what derivatives give us. Find the size of the fox population when the rabbit population is a maximum, meaning when the rate of change of the rabbit population equals 0, when the derivative equals 0. The rate of change of the rabbit population was dx dt, right? The rate of change over time. And we said dx dt, when we set that equal to 0, we're going to get x equals 0 or y equals 1/2. That's what we did in part A. So look, when the derivative of the number of when the rate of change of the rabbit population equals 0, that means the rabbit population is at a maximum. When the rabbit population is at a maximum, y equals 1/2. In other words, there are 50 foxes. And the size of the rabbit population when the fox population is at a maximum is going to be taking the rate of change of foxes, setting it equal to 0, right? Because that's our turning point in our graph, the derivative, when it equals 0. And we know that, well, that's going to give us y equals 0, but it is also going to give us that x equals 5/6. In other words, 833 rabbits. So when we have a max number of foxes, there's 833 rabbits. These foxes are thriving at 833 rabbits. When we have a max number of rabbits, meaning the rabbits are thriving, there are only 50 foxes. Okay. Now, let's use technology to verify our answers to parts B and C and describe the change in the populations over one cycle. Okay, so one cycle meaning one up and down. Now let's use our Euler's method. Again, I'll just use a step size of 0.1 so I don't have to drag it out too much, but remember, smaller step sizes lead to more accurate approximations. So where am I? I'm right here. We said t, x, and y. All right, our initial time 0 we had, I'm going to jump back here, at time 0, 750 rabbits and 100 foxes. So 0.75 and 1. 0.75 and 1. I'm going to increase by 0.1. So I'm going to say this equals the previous number plus 0.1. Enter. And let me just drag this out. I don't know how long one cycle is going to take, so I'm just going to drag it and we'll see what happens. And now here I need to use Euler's method to find all my x and y values. So this is going to equal our previous number plus, I'll use a step size of 0.1, 0.1 times, now what was our, oops, I need to put that times symbol in, so times, parentheses, the derivative for x was x minus 2xy. All right, so times x minus 2 times x times y. Computer's not that smart, and I'm actually going to put this in parentheses just in case. Computer's not that smart, you have to tell it times. And for y, y is going to equal previous y value plus 0.1 times parentheses. What was our formula for dy dt? 1.8 xy minus 1.5y. So 1.8 times x times y. Let me put that in its own parentheses. Minus 1.5y. 1.5 times y. Close parentheses. You know what? Let me put that in its own parentheses as well. And hope I didn't make any errors. Sweet. All right, and look, it said initially the rabbit population, we said initially was decreasing. Look at that, from 0.75 to 0.675, from 1 to 0.985. We said the fox population was also initially decreasing. All right, let's find out what happens as we change these numbers. Just drag these columns down. Remember, as we drag the next one down, our x values are going to change because x and y, they are dependent on each other. Look at that. All right, let me see how far down I want us to drag this. Okay, so let's go to t equals 5. I know it's going to kind of seem like a lot, but let's do that anyway. So I'll stop here. Keep dragging down my x and my y. And we're just going to analyze. We're going to make some graphs. All right, so I'm going to make that circular graph with just x and y against each other. This, and then insert chart. Boop. Oops, I should have dragged it up. Aha. And then I'm going to do the same, similar, but with t on my horizontal axis. Oops, I should have dragged this up. Okay. Create this chart. All right, and let's take a look here. We can verify those numbers like we saw in our intro problem right here. Okay, so let's analyze this graph. Okay, initial numbers we said were, initial numbers, 750 rabbits and 100 foxes. That is this point right here. That's why this point is kind of all by itself out here. We said both populations were decreasing. So look, our x values are going to the left and our y values are going down up until, about here-ish. Then our x values start to increase while our y values continue to decrease. So around y equals 1/2 or so, our x values start to increase up until we reach, whoops, hang on one second. Sorry about that. Yeah, so until the y values are at 0.5, then our x values start to increase. Meanwhile, our y values are still decreasing up until, about here, right? Then our y values slowly start to increase again. We will notice this 1/2 and 1 corresponds with these this equilibrium point that we got right here.